Hi everyone, thank you for joining us for the Encode Polkadot Inc. Bootcamp. We're really excited to see so many of you here to learn. So very quickly, I'm Rebecca, I'm from Encode Club. I'm quickly going to go through an overview of the bootcamp and a little bit about Encode Club, and then I'm going to introduce you to our speaker, who I am inviting up onto the stage so you can see him, and we'll very quickly get into workshop number 1 because I know you're all here to learn. So, for those of you who don't know, Encode Club is a global community of developers, professionals, and talented students in emerging tech. We run educational programs to help you advance your careers. So, what that means is currently we're running an education series in the Polkadot ecosystem. So, we've just finished our Educate, which was focusing all around topics in Polkadot 2.0. So, if you're interested in things like asynchronous backing, core time, Polkadot's Jam, then check out the recordings of those sessions. Currently, we're in the Polkadot Inc. Bootcamp, which of course is starting this week. And coming up, we also have a hackathon and accelerator in the Polkadot ecosystem. So really exciting things happening. So the bootcamp consists of 7 workshops running over 4 weeks. The overview of the workshops is here. I'll also post it in the Discord, so don't worry about keeping notes. You'll be invited to all of the workshops individually. But as a little overview, we're going to be looking at cross-chain contracts, security best practices, as well as doing some introductory and advanced Inc. courses. So there's something for everyone. So a little note before we get started. If you want to graduate from this bootcamp and receive a certificate saying that you've graduated from the Encode Club Polkadot Inc. Bootcamp, then you need to do 2 things. You need to attend the workshops live and you need to attempt the bootcamp homework. If you don't attend workshops live or if you don't attempt the homework, you may receive a certificate of attendance, but not a graduation certificate. So we heavily encourage you to attempt to graduate because we love to see as many Encode graduates as possible. So the homework, very quickly, is very open-ended. It basically entails, after each workshop, we want you to try and implement something based on the session that you've just seen. This could vary. This could mean forking and running some of the code that you saw if you're a beginner, or it could mean writing something of your own. As I say, this varies depending on what level you are and how confident you are in writing, but that's up to you. We also want you to keep a learning journal by posting very briefly about what you're learning, so either on Twitter or in the Discord, with just some details about what you've learned in the session and what you've tried. So this could literally be, after the Intro to Inc session, I ran this contract and this is what happened, just so that we can see that you're actively participating in the bootcamp. So that is all that I want to tell you. So I will stop sharing my screen and I will pass over to Luca so we can begin our first bootcamp session.
Cool. All right, so let's begin with this. This is going to be the first session of the bootcamp. We're going to start with an introduction to Inc. So first, let me introduce myself. I'm Luca. I work as a dev engineer at Papermoon. I have also worked as a developer. I used to work in Solidity and different solutions in the EVM world. I also work in different blockchains. We're doing different programming languages. And I have also participated in some projects with Inc. I have built some payment solutions, a multi-sig, and also with some colleagues, we did some security research and some dev tooling for it, okay? And let me tell you that even though it's a kind of new language, it is like pretty cool and the developer experience is smooth. So it's going to be fun. All right, so the agenda for this workshop will be something like this. We're going to start with writing smart contracts in Polkadot to understand the context. Where are we going to deploy the smart contracts? Where do they live? All of that. Then we're going to explain the Pallet contracts. Then we're going to understand how we actually develop smart contracts within. Then we're going to go through testing. And finally, we're going to do a live demo of the whole process. We're going to write a contract, compile it, test it, deploy it to a live chain, and interact with it, all right? So first, let's go to smart contracts in Polkadot. And in order to do this, first we need to define what are smart contracts, okay? Here you can see a definition. This is literally Wikipedia's definition, but the key takeaway I want you to take from here is that smart contracts are just sandbox programs that can be executed on the blockchain. That's it. It's a piece of logic, a piece of code that can be run in the blockchain. And in our specific case, it's not for any blockchain. It is for substrate-based blockchains, all right? And now you may wonder, okay, but what's Substrate, all right? So Substrate is basically a framework that allows people to build blockchains. You don't have to do everything from scratch. You can use some tools that this framework provides you, all right? And this framework has an opinionated idea that a blockchain consists on two components, all right? It has the client stuff that you can see here, but this is basically everything that has to do with networking, the database, the transaction pool, all of that, all right? And the other component is the runtime, and this is what we want to pay attention to. The runtime is the actual logic of our blockchain, all right? It's the state transition function. It indicates, it gives us the rules of how we're going to go from state A to state B, okay? And now, how do we build these runtimes? We can theoretically build everything by ourselves, but there is a framework that provides us with modules that can be reused to build this runtime, okay? So these modules are called pallets, okay? And each pallet bundles like certain functionality. So there's a huge collection of pallets that are already built, so we can just choose and pick whatever pallet we need, do some configurations, set some parameters, and we can have a runtime working for us, okay? And you may say, okay, but why do I care about pallets if I just want to write smart contracts, okay? But we need to know that when we write a smart contract and we want to deploy it to these substrate-based chains, we need a specific pallet to be included in these chains so they are compatible with smart contracts, okay? In this particular case, we need to have the contracts palette in our runtime so smart contracts are available, okay? So in Substrate, there are two main smart contract engines that we can have in our runtimes, okay? We can have something pretty similar to Ethereum, which is like EVM contracts. You can write Solidity, compile it, and deploy it in there. And we have the Pallet contracts, okay? Which is the topic of this workshop, okay? Just to realize where we're going to deploy our smart contracts. Our smart contracts are going to be deployed in the Pallet contracts that is inside a runtime, and this runtime is inside a substrate-based blockchain. Okay. So now the Pallet contracts, okay? We need to understand that the Pallet contracts is the execution environment, the execution engine that is going to take our smart contract and let us interact with it, let us deploy it, store data, all of that, okay? And it implements some functionality. For example, it provides us with gas metering. This means that for each program and for each execution, we're going to know how much gas it took to execute that, and we can charge users for that. Also, this pallet is agnostic of the language that we use to write the smart contracts. So let me explain this more in detail. This pallet accepts smart contracts that are compiled down to WebAssembly, which is like a binary instruction set, all right? So you could write your contract. For example, there are a few frameworks like Ask, which is based on assembly script, something similar to TypeScript. You can use Solidity with a particular compiler, which is called Solent, or you can use Ink, which is written in Rust, and it's compiled down to WebAssembly, okay? And this is important because if you wanted to, I don't know, write a contract in C, for example, you can do that. If you can compile it to WASM and provide the specific API that we need to interact with it, you could actually do it. You could even write your smart contract directly in WebAssembly, and that will still work. I have done that. I do not recommend it, but it's possible. Okay. So basically, the Pallet contract is the environment that provides us with all the functionality that we can access with our contract. Okay, we can read the state of the blockchain, we can set the storage, we can know who has called this method, we can transfer funds, we can do everything through this interface. Okay, yeah. So now we're going to begin with Ink specifically. All right. So Ink, this is the formal definition of Ink, right? Ink is an embedded domain-specific language that you use to write WASM smart contracts in the Rust programming language, okay? Let's break this down. We first said that this is an embedded domain-specific language in Rust. This means that Ink is not a new programming language, okay? It is Rust. The difference is that it's a subset of it. I mean, we don't have all the functionality of Rust, and we also have some new things that help us in this specific use case, which are smart contracts. Because it is Rust, we have all its benefits: memory safety, type safety, the tooling. We can use the exact same tools that we can use for writing regular Rust. Rust Analyzer, Clippy. You can import any crate, well, not any crate, but if your crate can be compiled in the no std mode, you can use it in your smart contract. Also, the developer community for Rust is huge. There are tons of Rust developers. The documentation is pretty good. So we inherit all of that for not creating a new language. And also, it compiles to WASM, to WebAssembly, which is with the Pallet contract needs, and this instruction set is fast, is secure, and some more things. All right. Now, this is probably for what you came from, which is seeing code, understanding, and how to write this code. Okay. This is the basic structure of an Ink smart contract. Okay. You can see here that we have a bunch of macros. But these things that you see here are macros. And what these macros do is that they perform a lot of stuff under the hood, okay? But we do not need to care about. These are performed in this way in order to make the developer experience easier. We can just take a quick look about the structure. First, we have this huge macro that seems confusing, but this means that when we're writing regular Rust, right? If you compile Rust in your computer, it's going to compile it down to the architecture of your computer, okay? But in this case, we are compiling to WASM, okay? And in this environment, in the WASM execution environment, we don't have access to the file system of the computer, to the input and output, networking. So this means that when we are compiling to WebAssembly, we do not want to include the standard library of Rust, because this is going to add a lot of code that we cannot use, so it doesn't make any sense to make the code bigger. Then we have the Ink contract macro, which decorates our module, and this is the skeleton of our smart contract. This is going to do all the APIs and configurations needed to interact with the Pallet contracts, okay? And we have a few sections in our contract. We have the storage, which is where we are going to define all the fields, all the state variables that we want to store in there. Let's say we can have like structures, primitive types, whatever you want in here. Then we have the methods that we can call, where we have the constructors that are used when you build your contract, and the messages, which are the ways that users have to interact with the contract that's already been deployed, okay? Now we're going to go a little bit deeper in each section so we can understand it better, all right? So we are going to start with storage. As we mentioned, in this structure that you said, which is decorated with the Ink storage macro, is where we are going to store everything that you need for your contract, for your use case. So you can use simple types like booleans, U8, integers, tuples, arrays, everything that has a static size, okay? You also have some substrate-specific types. Just to clarify this, when you are writing your blockchain, your substrate runtime, you can define certain types like this. For example, the account ID. And this is which kind of address our contract will have. The balance of our contract is going to be a U20, a U64, a U128. All these definitions are made at a substrate level, and we inherit them from our smart contract. Okay. Also, we can have data structures like Beck mapping, betray map, hash map, and more, because you basically can create your own data structures. You can import other ones. You can do whatever you want here. But now, as you know, smart contracts, deploying smart contracts, using smart contracts is not free, because it consumes gas, it takes space in the blockchain, so someone has to pay for it. Okay, so it's important to understand how the data is stored in order to make it a little bit more efficient. Okay, so the storage of our contract will be in a key value database. Okay, it means that for a certain key, we're going to store everything in there. These values, for example, when you see a boolean or a UA, it's not going to be stored like the same way. This is going to be encoded using scale. You don't really need to know this, but probably if you want to do some low-level stuff or mess with something in there, you should review the scale encoding, okay? But let's just say that our data is going to be encoded in order to be stored. And an important thing is that this whole struct that we define, which is going to be our storage, our state, is going to be stored just under one storage cell, okay? It's going to take the key, the zero key, and try to store everything in there. And you may say, yeah, but why do I care about this? Just store it, and then I'm going to retrieve it, use it, and that's it. But the thing is that if your state is small, you don't have much of an issue. But let's imagine that we have a message that is going to just flip the value of this bool, right? It doesn't matter that it's going to modify this value. For the way that ink works, when you want to execute the message, it is going to load the whole state, is going to decode it and load it in memory, all right? So if you just want to modify this bool, it is going to load everything, the U32, the Beck, and this specific type, okay? So you have to be careful when having types like this Beck. Why? Because as you see in there, a vector, you can just append values and it doesn't have a maximum value, okay? It's an unbounded Beck. So if you let your users push values to a Beck that can grow indefinitely, you can actually break your contract, because the ink environment only allows you to load to memory, I think it's up to 16 kilobytes or something like that. So if you make this state bigger than that, you're going to have problems, okay? But there are ways to optimize this. This is not like something that you cannot solve. There are certain types, for example, this lazy that you can see here, that allow you to move the value to a different storage cell, okay? In this case, where we have this lazy modifier and a certain type, we don't care about the type, okay? What this does is that it just stores a pointer in the actual zero key, and if we want to access the value, we have to do it manually, right? So we have to say, okay, pointer D, go search for the value and bring it back to me. So what this does is that if we have a huge structure in there that is only modified in one message, we can only load it in that case, and we don't have to do it in all the other cases, all right? I know this is complex, But as you start writing code and learning about ink, you will realize that this is like a very important step to take into account, all right? Now, here we can see a storage example that we can have. We can store, for example, a Boolean. We can store like a vector with some entries. Values that are optional. It can be undefined, which is like none in Rust, or you can have an actual value in there. We have this specific type, which is called mapping, which is pretty interesting. What this type does is that you can, for example, here we are going to use a key, as a key, the account ID of a user, all right? And we're going to store a user84. So imagine that we have a message that we only want to modify let's say this is a balance, okay? We just want to modify my balance, okay? So imagine that you have to load the balances of all your users into memory just to modify one. It doesn't make any sense. So what this allows us to do is that we can only load the things that we're going to use. So we can ask, okay, give me Lucas balance, you retrieve that, modify that, and that's it. You modify only this particular key, okay? Now, we're going to move to the next section, okay? Every contract needs a constructor. These constructors are used to initialize the contract and get the state initialized, because as you see here in this struct, we do not define the value, we just say the type. So in the constructor, we need to say, okay, this value, this field is going to start with this value. So in your contracts, you need at least one constructor. As you can see here in the function definition, constructor return an instance of this structure. So you can see that we are initializing the number field here. An interesting thing about ink is that you can have multiple constructors. For example, here we have a default constructor that initializes the number with a default value, which in the case of a number should be 0. And we have another constructor that we can define the actual value, okay? And this is basically it for constructors. Then we have the most interesting part, which is messages. Here's where all the logic of your smart contract is going to be implemented. All your users, all the people that is going to interact with the contract is going to do it through the methods that you expose to them, okay? At least your contract to be compatible and to be deployed to a blockchain must have one message, okay? And we can differentiate two kinds of messages. Just clarification here. What you see here, this self-reference that we have here, is a reference to the state of the contract, okay? So you can infer that if we only have an immutable reference to self, this is going to be a read-only method, okay? And if we get a mutable reference to the self, to the state of our contract, this can mutate the state and modify it, okay? So the methods that modify the state, they execute certain action on the contract should be mutable. Then, when we are executing this logic that we define, it's not always going to be successful. And we need a way to indicate users that something happened, okay? In blockchain, when an error happens or something fails, we need to roll back the execution. We cannot be, let's say we modify something here, and when we start a function, we cannot leave it in the middle. We need to commit the whole operation or just roll back everything, okay? These reverts can be done in two ways in ink smart contracts. The first one, and the ugliest one, is just panicking here, which is not recommended. But if you find a panic in your contract, it's going to revert, okay? Now, the idiomatic way of reverting a contract is using custom errors, okay? And here you can provide information to the user so they can understand what happened and why the transaction failed, okay? So let's imagine this scenario which we have a implementation similar to an ERC20 token, right? So here we define two errors, which is like insufficient balance and insufficient allowance, okay? This method is called transfer from, all right? It receives three parameters, from, to, and a value. What this is trying to do is to take some money from the from account and transfer it to the to account, all right? But what we need to check before doing this is that the one who is calling this function is allowed to actually perform this transfer, because he's taking money from someone else's account, okay? So here we're checking who is calling the function with this self and caller. Then we are checking how much money is he allowed to move from the from account, and if this amount is less than the value he wants to transfer, we should revert the contract and return an error, okay? And this is what we're seeing here. These errors are not, they do not come out of the box by Inc, okay? So you have to manually write it by yourself, like you can see here. They are user certified. If you really wanted, you could just, instead of returning an error in here, you could just return a number or a string, but that's not recommended, all right? This is the best way to do it, because it's the way that you can provide more information to the users, okay? And then we have events, okay? Events they don't really modify anything on the actual logic of your code. They are basically used for indicating off-chain people, like someone who is listening to your contract, someone who is waiting for an execution, to know what happened, okay? Remember that when we submit a transaction on chain, this is not something synchronous that we do. It takes time, because we build a transaction. We send this transaction to a node. This node has to build a block, then propose the block, execute the block. So it takes time, and we cannot know like instantaneously what happened. So the best way of doing this is with events, okay? So here's the same example before, but in this case with events, okay? We're doing the same thing. We're trying to transfer funds from one account to another. Here in the middle, we will perform all the checks, everything. We will do the actual transfer, and if everything went successful, we can emit this event, okay? For example, I have used events in user interfaces, in websites. You let your users submit the transaction, and you show them like a loading screen while you're waiting for the event to be for the transaction to be executed, okay? And you just submit to the event and keep waiting in there. So when you get the event in your user interface, you can actually indicate to the users, okay, your transfer was successful. You transfer money from this account to this account with this value. Also, another use case that is pretty important for events is for indexers. I don't know if you have ever used indexers, but you have the graph, subsquid, subquery, and a bunch of them. So basically, what indexers allow you to do is to listen to all the events that happen in the blockchain for a certain contract or for multiple contracts, and you can build like an off-chain database to provide you information. So this is also done like for data analytics. You can do it for displaying more information on your website and many things, okay? So the ideal path, the ideal structure of a contract is to have an optimized storage, then you have your constructors, then when you build your messages, you have to perform all the checks. If something is wrong, there's a condition that's not met, you should handle all of this with errors which have an indicative name, which a proper description, and if everything is successful and you modify the state, you should emit an event, okay? To let the outside world know that something happened. Okay, now we wrote our contract, we have we understand like a little bit about the structure, but we need to test it, okay? And there are two we have like two ways of testing in smart contracts, okay? We have off-chain testing, which is a test similar to the one that we can see here, which it runs the test in a simulated environment, okay? It doesn't create like a blockchain node and submit a transaction. Everything is done in our computer in the same process. So let's analyze this, okay? So we use the inc test macro to define this kind of tests. And here we can say that we are creating a new contract with the default constructor, and then we can call the method, okay? So if you remember, using the default constructor on a Boolean gives you a false, okay? So if we call the get function, we're going to get false. Take into account that all of this that you're seeing here is synchronous code, okay? So it's everything in here. The same here happens here. We create a new contract with the new constructor. We read the value, then we call the flip function, and we check again, and obviously the value has changed. Now, the environment, these APIs that I mentioned earlier, that the Pallet contracts provide you, are not available in here. So everything is mocked around. So if you want, for example, to simulate that a different person calls the contract, you have a few methods in here to set those values, okay? So just to recall, this is probably the first tests that you do should be in here. Is just more about the logic, but it doesn't include the whole ecosystem, the whole process that you really need to do in a real environment. Now, the other approach that we can take for testing is end-to-end testing, okay? And as the name says this, we go from the contract to the blockchain node. So we're going everything in here, okay? So imagine that for running these tests, what the framework is going to do is going to run an actual blockchain node in the background that's going to receive we're going to deploy the contract to that node. We're going to call the methods in there. Just so you understand, let's go through this step by step, okay? So in this default works function, which is mapped with an inc test macro, here we only define which call are we going to use, which constructor, okay? Here in the when, you can see that we have a client, okay? This client is actually connected to the WebSocket of our node, all right? So we are going to call the instantiate function, which is in charge of deploying the contract and creating a new one. This transaction is going to be signed by a certain account, which in this case we are using Alice, which is like a test account with a non-private key, and it's going to call the constructor that we define up here, okay? You can see that this is an asynchronous operation because we're awaiting here. So we constructed the instantiate transaction and we deployed to the blockchain, okay? And here we're waiting for a result. In the background, there are happening so many stuff in here. So we are preparing and encoding the transaction date. We are signing the transaction with the key that we provide here. The transaction is sent to a blockchain node. The blockchain node has to take this transaction from the transaction pool, put it inside a block, build the block, finalize the block, execute it. There are so many things that are going in here, and this is the most similar case to a real scenario, okay? After the contract is constructed, here you can see that we are just reading the state, okay? We are connecting again to the node, we are calling the get method, and we are getting the value, right? I know this was like a lot of information, but now we're going to go step by step and doing everything from scratch, okay? So you can see my terminal there, right? Can you see my terminal there?
Your terminal. Sorry, I was just joining the stage again. Yep, we can see your terminal. Good.
Cool, perfect. So in order to develop smart contracts in Ink, there's something key that we're going to use, all right? This is called cargo contract, okay? Here you can search it in GitHub. It's under use Ink cargo contract. This is a CLI. Well, here you can see the installation. You can do it by yourself, all right? It's a little bit small. I can make it a little bit bigger. There. So cargo contract is a CLI that will help us to create Ink projects, build our contracts, even deploy it, interact with it, okay? So now we are going to start with creating a new project, okay? We're going to do cargo contract, new flipper, and this helps us create a new contract, a new project, all right? Let me make this bigger. So as you can see here, this is the exact same structure as any Rust project, okay? We have a lib.rs file, which is basically our code. We have a cargo toma with our dependencies, and a cargo log with the log versions and all of that. So first in the dependencies, you can see that we have just one dependency that is Ink, okay? This includes all the macros that we saw in the code, all the interface that are built under the hood to allow us to interact with this environment, okay? Then we have another dependency, which is like Ink-HD, which is going to be just for running this kind of tests, all right? So this is the same code that we saw earlier. This is our Flipper smart contract. I'm going to start building it because it takes some time. So when we build our contract, we have two choices. We can just run cargo contract build, which is going to do it in debug mode. But when we want to actually build it for deploying on chain, we should run it to the release flag, because the WebAssembly is going to be optimized, it's going to be smaller, it's going to remove a bunch of debug symbols and many things, okay? This will take a little bit, but we're going to compile our contract, okay? When we compile our contract, just let this compile, right? When we compile our contract, we're going to obtain 3 files, okay? The output is going to contain 3 different files. We're going to have a .wasm file, a .json file, and a .contract file, okay? We're going to see it just in a minute. The important thing about these files is that in the blockchain, we are only going to store the WebAssembly, the .wasm file. And this is basically all the logic of our contract. But the .json file is so important because it contains all the metadata. So here we can see that the 3 files were generated, right? So when you compile your contract, you can see it in target, Ink, and here they are, right? The wasm, we cannot see it because it's just binary. Then we have the JSON, which is the metadata file. If you have experience in like EVM or Solidity, this is similar to the ABI you get when you compile your contracts. The information we got here is, here we only have like information with which version of Ink we're using, which version of the Rust compiler, if we build it in debug or release mode and stuff like that, okay? But the important thing is here. We can, with the metadata file, we can know which methods are available, which are the constructors. For example, remember that in this contract, we have 2 constructors, right? We have the new, which receives a value, which is a Boolean, and the default one, okay? If we check the metadata, we're going to see the exact same thing, okay? We have here our constructor called new, and with an argument that is a Boolean, right? This is, you really need this file to understand how you can interact with the contract, okay? Because remember that WebAssembly is just binary, and that's uploaded on chain. you can read it on chain, but you cannot understand like what's going on there, okay? So you really need this file from your UI, from the CLI, from everything, for anything you want to interact with the contract, you need to have this, okay? And the flipper.contract file is basically both things in one, okay? We have the WASM here, which instead of being in binary is just in hexadecimal. And then we have the metadata file, which is the same thing, but it's not formatted because the file is too large, so VS Code doesn't format it, but it's the same thing. We have all that we have in the JSON file is also in here, all right? So before deploying this contract on chain, what we should do is run the tests, okay? Yeah. So here we have the same test that we showed before. These are the off-chain testing, which are done with the ink test macro. And in order to run them, we have to do cargo test, okay? As you realize, this is compiling everything again. And you will say, like, okay, but why? And if you also check here, it has more dependencies. Do you remember this macro that we defined here? When we're actually compiling our tests, all the code is being compiled with this feature on, right? Because remember, this runs on our computer. So it needs to be compiled to the architecture of our computer, and it also includes the standard library. Because when we are debugging and when we are testing, we can add some messages that we can print to the console or stuff like that. So that's why this is being compiled again, all right? And while this finishes compiling, we can check that here we have the end-to-end tests, all right? And in order to run these tests, we're going to run the same command, like cargo test, but with this feature enabled, all right? So once this finishes, we're going to see that the tests were successful, all right? Now, once your tests are ready, yeah, we can even add like here. We're going to add a message here, okay? So we can say ink and yeah, print line, no. The flip method is called, we're going to see a message that calls flip, okay? So this is helpful when you have like different paths that your message can take, or you can even print like values or stuff like that in order to debug it, okay? So to see this message, we're going to compile the contract again. So now, how we can actually deploy our contract? We can do it in our computer, in a local network that we can run. We can also use testnets that we have over there. So the first thing I'm going to do is to run a local blockchain in my computer, okay? So here I have this blockchain, which is running in my computer, and it has the Pallet contracts in it, all right? So this is like a regular blockchain node, right? So once this is running, there are different ways we can deploy these contracts. The easier one, and the one that I recommend the most, is just like taking these files. We can go to this website, which is called ui.use.inc, and here in the dropdown, we can choose where we want to deploy our contract, okay? We could use this to deploy on a live network like Alef0, Astar. We can do it with test networks, or we can do it to a local node, which is the thing we're doing now, okay? So we want to add a new contract, upload a new contract, and we're going to drop the .contract file in here. So here you can see that this took the .contract file, which has the WASM and the metadata, all right? It understood that it has two constructors and two methods, and it's letting us deploy it now, okay? So we have to choose which constructor do we want. We're going to select new, true, next, and we have just deployed our contract on chain, all right? Take into account that this was like super fast because the node I'm running is optimized for testing, okay? So it's very fast. But when you're doing this to like a testnet, this is going to take a few seconds, all right? So here we can see that if we call the get method, we get the value that's true. If we call flip here, the values should have changed. We can see here the events that were emitted, and the value has changed, all right? So you can use this to interact with any contract that you deploy or that you have the metadata, all right? Let me show you something different. There's another way of deploying the contract. If you do not want to use the UI, you can do it just from the CLI. So we can do something like this. So we're going to use the cargo contract CLI. We're going to use the instantiate method. Here we have to say who is going to sign the message. In this case, we're using Alice because this is like a test node. But if you want to do it in a regular blockchain, here you will insert your 12 words, right? Your private key. So we're just going to use Alice. Here, because we are like deploying a new contract, we are going to define which constructor we want to use, which we want to use the default, and then we execute the transaction, okay? We have to confirm the transaction, and it was executed, all right? So here we can see these events are from the blockchain, not actually from just our smart contract. And here is the contract address, right? With this address, we can come to the UI, and instead of deploying the contract, we can just interact with it, okay? We have an option that says use on-chain contract address. So we can paste the address here. And here we have two options, all right? Because this contract has the same metadata as the one that I deployed before, the metadata was already stored on the web browser. So here it recognizes it and tells you, okay, do you want to use this metadata? We can just leave it as it is. But if we didn't, we can just upload the JSON file here and we can interact with it. So we add the contract, and here we have the contract that was deployed from the CLI, and it should have started in false because we use the default constructor, all right? Yeah, so if you want, we can try to deploy to a testnet. For example, we can use this one, contracts on Rococo. So this is one of the testnets that we have in Polkadot. So we can do this. It's the exact same process. You upload the new contract code. Here we will drop the file. Here we can call the constructor. And now it is going to prompt me with my actual wallet to sign the transaction. Because this is a real blockchain, so we have to pay some fees, right? I already have some tokens, but in your case, you probably won't. So you will have to first create a wallet. I can recommend like Talisman, Subwallet, there are some of them. And after that, you can come to this webpage, okay? I will share the pages after I finish with the workshop, so don't worry about this. But you can go to the faucet, you select the network, Rococo, the chain which we are going to use, which is contracts. You can paste your address in here, and you will get some tokens, all right? So that's done. We have just deployed this contract, and if we want to get the value, it is in false. If we want to interact with it, same thing. We get the transaction, we have to approve it. We're waiting for the whole process, like waiting for the transaction pool, building the block, all of that. And this can take a few seconds. Okay, in the meantime, I want to explain you something that's, from my perspective, very interesting. If you have deployed contracts in any EVM chain, if you deploy the same contracts like 10 times, the 10 times the contract code, like the binary, is going to be uploaded to the chain, okay? In the case of Polkadot, that's different, right? So we're going to use this web page, which is called Polkadot.js. This allows us to interact with any substrate-based blockchain. For example, let's take, this is taking a while, so let's go back to our local blockchain, right? So here we deployed contract with this address, right? We can check where this contract is stored on the chain, right? So we can use, for example, here, contracts, contract info, and here. You don't have to understand everything, it's just to make a point, all right? So you can see that this contract has a code hash, all right? And this code hash is like a key where the code of the contract is stored. So let's imagine that I send all of you this Flipper contract, all right? Like the same .contract file. And all of us deploy to the Rococo testnet, okay? The good thing about Polkadot is that it's not going to store this 10 times. It only does it the first time under this key. So it takes the WASM, makes the hash out of it, and stores it somewhere, okay? And each time someone creates a new contract with the same binary, with the same WASM, it just points it towards this code, okay? You don't have to keep adding things to the state of the blockchain because you are basically repeating the same thing, all right? What you have to take into account is that just the code, just the logic is reused by everyone, but the state, the state is for each contract, so that's independent, all right? I think I have a few more minutes, yeah. So here we can check another example. Give me 1 second. Yeah. So this is more complex contract. So in Polkadot, we have a different standard than the ERC20. It's similar, but it has like certain tweaks. So here is called PSP22, all right? So this is the implementation of the PSP22 contract, okay? And here you can see that the contract is split in a few different files, right? So you have data, errors, events, testing, traits. So we can go through this kind of fast. So basically, data is going to include everything related to the data that we're going to store in our contract, all right? The state. So here we have like total supply, balances, allowances. Here we have a few methods that are used to construct this state. Then we have a file specifically for the errors. So we can have like custom errors, insufficient balance, insufficient allowance, and a few more of them, okay? Then we have events, which are emitted when something changes in the contract, which in this case is basically transfer and approvals. We have something interesting, which are traits, all right? If you have used Rust, you know that traits, if you don't, also I can explain it. Basically, traits are like interfaces, all right? You only define the signature of the functions that need to be implemented to adhere to this trait, okay? So here we say, if you want to adhere with the PSP22 interface, you need to at least implement these methods. So we're going to need like total supply, balance of, allowance, transfer from, approve, increase allowance, and a few more methods, all right? So when we check our contract, like the actual implementation, here we see that we have a few structures, the events, the actual storage of our contract, which uses the data that we have just imported. We have a name, we have a symbol, we have decimals, and here we have all the functions, all right? we have just one constructor that takes the initial supply, the name, the symbol, the decimals, and here we build like the initial state, all right? Also, something interesting is that we can have like helper functions, all right? So if there's a function that is not decorated with a macro, like this one here, it's just a helper function. So you can call it from wherever you want, right? And here, this was just for creating the structure. But here, we're implementing the interface that we mentioned before. So this means that our contract is going to implement the PSP22 trait, all right? So here we're going to take all of the functions that we got from there and actually implement the logic here. The read functions are just like reading state and doing things like that. Then we have the transfer function, which is like a mutable function, so it's going to change the state. And this is calling an internal function, which is called transfer, okay? Here we are sending the parameters, like in the from parameter, we are sending the one who is actually calling the contract. This is the way that we access that. We are calling the function, which is internal. And here we're performing like all the checks, okay? This is like a real contract, so we have errors, we have events, we have everything in there. If the balance is not enough, we have insufficient balance. If the approval were enough, we also have the same thing. For example, here we are using like saturating add instead of just using the plus icon, because this allows us to do not have overflows or underflows when we're performing math. So yeah, I think that's a cool thing to wrap up. I know it's been a lot of information, so yeah, we can leave it here. So yeah, here you can find the slides from today. This is my Twitter, my Telegram. You can contact me in there. And yeah, I don't know if there are some questions, something you would like to ask.
There's a few questions in the questions tab. You're able to see the questions tab on the live storm.
Yeah, I can see them. Okay. Yeah, so the document, here you have the QR to the slides. So yeah, this is the document. Then, which wallet do I recommend? Probably you can use Subwallet, this one, Talisman. Both of them are pretty good, so it's just on you. You can just do your research and decide from yourself, okay? So this uses pointers to save block space. Is that true? Not actually block space, it's just only on the runtime, all right? So, I mean, for more information about that, you can go to the ink documentation here. In the storage section here, you can understand it a little bit better and a little bit more in depth. So here are the same screenshots, and you have a more descriptive explanation on how this is performed. But this is basically something like this. So you load everything into memory, or you can just select what you like. You can nitpick what you want to load, right? But you're not saving block space. You're occupying the same space on the chain. It's just on runtime. I don't know if this answered your questions, Adam. Right. Code hash. Okay. Amar said there that I'm talking about the code hash. Yeah. If we were talking about the code hash, yeah, that saves space. That saves block space, because we are not like saving the Wasm smart contract all the time. So it's just once.
There's a couple more questions in the questions tab, and then we'll wrap up very soon.
When do you struggle? All right. So Hasni, I think I'm pronouncing that. If not, I'm sorry. And that definitely depends on your use case. But for example, like struct, beg, bitremap, hashmap, these four, they have this package behavior. So everything is going to be stored under the same storage layout. And if you want to use something that allows you to bring data on demand, you should use like mapping. There's another one called Storage-based. So you can find those structures. Yeah, probably here in the storage and data structure section, you can have more information about that. Then, okay, we have Edgar's question. He said, what's the name of the testnet? So the testnet is called Contracts Rococo. I can also send you the faucet link here in the chat. That's the faucet. This is Ink's documentation. And yeah, this is the CLI that we were using. For the homework, what they could do is, this is another page here, which is called like Ink examples. This is in the original repository of the Ink smart contract. So what you could do for the homework is try to take one of these contracts, like you can try to understand them, see what they're doing. What I would say that you could do is take only one of these contracts, compile it, and try to deploy it to a testnet or to a local network, so you can actually understand like the whole process. Building it, reading the code, interacting with it, that would be cool.
Yeah, that would be amazing. And on the note of the homework, there's no pressure to do anything complex. We're not going to be grading homework based on level of complexity or amount of time spent on it. This is purely for you to make the most out of the bootcamp and to do something practical alongside the workshop sessions. Do what you feel like you can, and please do share what you're doing either on Twitter and tag us or on the Discord channel. Hopefully a few people were talking in the Discord channel during the session, so hopefully you can all find it. If you can't, I'm going to send the Encode Club Discord link, and you have to join the Polkadot Inc. Bootcamp role, and you'll see the Polkadot Inc. Bootcamp channel, which is specific to everything we'll be talking about to do with this workshop. So to get the role, when you're in Discord, on the top you'll see channels and roles, and you just need to select Polkadot Inc. Bootcamp 24Q3. I'm not sure if I can send pictures, but I'll try and send a screenshot. Oh no, I can't send a screenshot. It's in channels and roles, and join the Polkadot Inc. Bootcamp. If you can't find it, post in the club room and I'll try and help you. But make sure you join that, and I'll post all of these links that Luca has just sent in the chat. I'll put them all there, so don't worry about saving them. Thank you very much, everyone, for joining us for Workshop 1. Thank you, Luca, for our introduction to Ink and for kicking off our Ink boot. I'll write a note in the Discord about the homework and make sure I cover everything so that everything is clear. So don't worry about that. We'll stop here for today because we've run over time, but I will hope to see all of you for workshop number 2, which is in 2 days on Thursday at the same time.
Thank you guys for staying the whole workshop, and I hope this teaches something.
Nice. And we'll be posting the recording of this workshop, so if you want to rewatch any of Luca's demos, then this will be up tomorrow, so that's all good. Oh, didn't know you could have thumbs up emojis. Very fun. Okay, cool. We'll leave it there for today, and we'll see you all for workshop number 2 on Thursday. Bye, everyone.
Bye, everyone. Have a great day.